Hello and welcome to the first lecture of ENCS 6010 Advanced Applied Mathematics. This is Ali Sekman. I'm a professor of computer science here at Tennessee State University. Today we're going to talk about mathematical spaces. Let's get started. All right. So again, this is ENCS 6010 Advanced Applied Mathematics, and mathematical spaces is our topic today. So what are we going to talk about? We're going to talk about spaces. We're going to define what a space is first and the properties of spaces. We will focus on norm vector spaces and inner product spaces, and we'll talk about Banach and Hilbert spaces. These are very well behaving spaces. We'll introduce the concept of metric space, and we'll talk about topological spaces. Topological spaces concept is not very easy to understand, especially with the limited time that we have, but at least you will get a feeling about the need for topological spaces. And we'll introduce what a subspace is. We are not going to get into details of it, but you are going to see that a subspace is nothing but a space with some special properties. So here is the first big picture that we are going to drive today. I must tell you that, it may not be easy to find a lecture that gives that big picture in a single, class time. So we'll talk about Hilbert spaces. Hilbert spaces are very well behaving spaces. And then we are going to introduce Banach spaces. We will show that every Hilbert space is actually a Banach space. We will talk about inner product vector spaces. And we will see that a Hilbert space is an inner product vector space. And we'll talk about norm vector spaces. A Banach space is a norm vector space, and every inner product vector space is a norm vector space. And we'll talk about general vector spaces. This is the first picture that we're going to try to develop. Second big picture, we'll talk about inner product spaces. Think about R2, for example. What is the main concept in R2? In R2, you can define two vectors and you can define the angle between them. So inner product space has the concepts of angles. Then we have norm spaces. In norm spaces, think about a vector and the length of the vector. And a norm is simply some form of length of a vector. And we'll show that every inner product space is a norm space. We'll talk about metric spaces. In inner product spaces, we define angles, and then we have length in norm spaces. In metric spaces, we'll be able to define the distance between the points in the metric space. And then we have topological spaces, and there are certain spaces in which you may not define an angle, you may not define a length, you may not define the distance even, but you may define how close the points are. Basically, there is a concept of closeness or nearness. Topological spaces are all about that, how close things are to each other, okay? And then there are certain vector spaces that are topological, but there are vector spaces that are not topological as well. So we'll talk about the second big picture. So that's our task, to derive those two big pictures today. So let's talk about what a vector space is. A vector space is nothing but a set of objects. That's simple. So a set of objects. But it is not just random set of objects. In this set, the objects can be added together or multiplied by numbers. We call them scalars. So again, a vector space is a set, and the objects or the elements of that set can be added together, or the elements can be multiplied by scalars. Scalars are typically real numbers, but they don't have to be real numbers. They can be complex numbers, for example, or rational numbers, or generally any field. When we introduce the concepts of abstract algebra, you will understand better what a field is, but real numbers, complex numbers, rational numbers, these are just fields in abstract algebra. If the scalars are real numbers, we call them real vector spaces. If the scalars are complex numbers, then we call that particular vector space as a complex vector space, okay? But when you add vectors from the space or multiply them by scalars, they must satisfy certain requirements. We call them axioms. For example, in R2, if you have X in R2, Y in R2, if you have X in R2 and Y in R2, when you add them up, again, the added vector is what? In R2. So I know this is trivial, but you may have 1, X, you may have Y, and when you add them up, that's also what? In R2, okay? Or you can have X in R2, and then you may have a scalar in R, and when you multiply X by that scalar alpha, alpha X is also in R2. So here, a vector space, okay, so before we define the vector space, let's talk about some other concepts. A vector space may have additional structures, such as norm or inner product, okay? And this is really typical for infinite dimensional function spaces whose vectors are functions. And we are gonna talk about infinite dimensional function spaces soon. I know it sounds complex, but it is not that complex. And also, in many practical problems, we deal with a sequence of vectors. When you have a sequence of vectors, convergence becomes important. So we talk about the concepts of convergence, whether a sequence of vectors converges to a given vector or not, okay? So when we talk about convergence, we talk about proximity, continuity, and so on. And in order to allow those concepts, most vector spaces are endowed with a suitable topology, okay? For example, a topology is simply, as I said before, in topological spaces, a topology is a structure that allows to define being close to each other. So how do you define things to be close to each other? And such topological vector spaces have richer theory. For example, Banach space topology is given by a norm, whereas Hilbert space topology is given by an inner product. I know we don't know what a Banach space is or Hilbert space is, but we are going to learn soon. So basically, a norm is used to define the Banach space topology, and inner product is used to define Hilbert space topology, okay? So here's the definition. A set V is called a vector space over a field F. It might be, as I said, real numbers or complex numbers, when vector addition and scalar multiplication satisfies those axioms. First, vector addition. If you have two vectors, V and W, in this vector space, okay, or in the set V, then when you add them up, the addition is also where? In the same set. Okay, and then we have associativity, and if you have three vectors in V, W, U, you may add them up this way, or you may add them up this way. It will not make a difference. Or we have commutative property, and if you have two vectors V and W in V, whether you add W to V or V to W, doesn't matter. They are going to be the same. And also there's an identity element, 0 of V, such that you add the identity element to any element in V, it will be basically, it's going to basically not change anything. So V plus 0 will be what? V. And also there's an inverse element. For every element V in the set V, we have an inverse element such that when you add the inverse element to the original element, you get the identity element 0. Scalar multiplication also has axioms. So if you have V as an element of set V, and if you have alpha as an element of the field, when you multiply alpha and V, you end up with another vector that's also in the set V. Compatibility, well, when you have alpha and beta in field F and V as a vector in V, whether you first multiply alpha and beta or first you multiply beta with V and then alpha, it's not going to make a difference. Again, we also have this distributivity 3 and 4. And if you have V and W, and if you multiply by alpha this way or that way, doesn't matter, or this way or that way, does not matter. We also have an identity element. This is identity element with respect to addition. This is identity element with respect to multiplication, okay? When there is an identity element, I call it 1, and if you multiply V by this identity element, you end up with V. Okay? So basically, any set V that has those all 10 axioms satisfied is a vector space. A space is a set with certain vector addition and scalar multiplication properties. Okay, so what are the applications? Well, Fourier transform. I'm sure some of you have already used Fourier transform in digital signal processing, image processing. It's heavily used in engineering and science. And as a student, I used it for years. And as a professional scientist or engineer, I still use it. So we can analyze a signal, such as an audio signal. Think about an audio signal. We can analyze it in the time domain or in the frequency domain. And the Fourier transform of a function f is defined as this infinite integral. So this is your f in time domain. If you take this infinite integral of time domain signal, you are going to time domain function, you are going to end up with a frequency domain signal or function. So Fourier transform. And just to be in practical size, think about this as fx. As you see here, this portion, when you look at this portion, and when you look at this portion, they have two different frequency contents, okay? The frequency here is higher than the frequency here. And this is your time domain signal or time domain function, this one. And when you take the Fourier transform, you end up with this. If you look at that, we have two peaks, one here and then another one here, okay? So what does tell us? This tells us that the contents, time domain content here corresponds to this frequency, time domain content here corresponds to this frequency. So there's two pikes. So basically from time domain, you go to frequency domain. And clearly in the frequency domain, we see that there are two frequency contents in this signal, okay? So with the absolute value of the Fourier transform, we can measure the amount of the frequency. For example, the content, the frequency content for this particular frequency is high. The frequency content for this particular frequency is high, but the frequency content for a very high frequency is very low. Actually, there is no, and so on. Okay, so Fourier transform is very widely used. Again, it takes you from time domain to frequency domain. It gives you the frequency contents of what? The time domain signal. So what does this have to do with vector spaces? Okay, so let's talk about that. When we define Fourier transform, we need to also define when the transform is well defined. There may or may not be a Fourier transform of a particular function. So when we say well defined, you can define the Fourier transform of that particular function. So the Fourier transform is defined on a vector space. We call it L1. L1 is a set of functions from real numbers to complex numbers, as you see. F is a function from real to complex, such that the infinite integral of the absolute value of x is finite. Okay, so if you take the infinite integral, or if you take the integral of f of x over the real line, you get a finite integral. So Fourier transform of functions, the Fourier transform of a function is defined only if that function is what? In L1 vector space. Now, this is different than R2, R3. This is a different, totally different. The elements of R1, elements of this vector space are functions whose absolute integral over the real line is finite. Of course, to be more precise mathematically, I want to say that we are not considering equivalence class of functions that are the same almost everywhere. So, well, if you're a mathematician, you will understand better. There are functions whose absolute integral may be equivalent to each other or equal to each other, even though the functions are not. So we are excluding equivalence classes of functions from consideration for simplicity. Again, Fourier transform of a function f is well defined if f is in vector space L1R. L1R is a vector space whose elements are functions, whose absolute integral over real line is or are finite. Okay. All right. So how about another example? Do we know what a Fourier series is? Any periodic function can be expressed as infinite sum of exponentials. So any periodic function can be expressed as an infinite sum of exponentials. Okay. For example, if we say the period is 2 pi, we can have, okay, so when can we define those periodic functions? Well, when we say any periodic function, okay, we can represent with exponentials, infinite sum of exponentials, but the coefficients of those exponentials are well defined only if and only if the function belongs to L2 space. For example, if the period is 2 pi, and if the function belongs to L2 space consists of a set of functions. It's a set of functions whose energy over one period is finite. Again, you can have a periodic function, and you can have well-defined Fourier series coefficients of that function if and only if that function belongs to L2 space. Okay, and L2 is again a vector space whose elements are functions such that their energy in one period is finite. Okay. Well, if the function does not belong to L2 space, then the Fourier coefficients may not be well defined. Okay, so what did we see so far? For Fourier transform, the function must be in L1 vector space. And for Fourier series, in order to have the Fourier coefficients to be well defined, the functions must belong to what? L2 vector space. Okay, I hope it is clear so far. So what's a basis? I'm sure many of you are already familiar with it. Every vector space has a basis. Okay. So every vector space, infinite dimensional or finite dimensional, doesn't matter. They have a basis. Every vector in a vector space can be written in a unique way as a finite linear combination of the elements in this basis. Again, every vector in a vector space can be written in a unique way as a finite linear combination of the elements in the basis. Unique way is important, okay? And number of elements in a basis is the dimension of the vector space, okay? Basically, if you have infinite number of elements in the basis, that's an infinite dimensional space. Here is the simplest possible example. We are in R3. We are in R3, and then E1, E2, E3. E1 is 1, 0, 0. E2 is 0, 1, 0. E3, 0, 0, 1. These are the basis vectors. Why? Because if we get any vector in R3, any vector in R3 can be written as combination of E1, E2, E3 in a unique way. Okay, so this is the only way to represent P in terms of E1, E2, and E3. Any point in R3 can be represented by those linear combination of those three vectors in a unique way. Since we have three basis vectors, the dimension of R3 is, of course, what? 3. So let's talk about well-known vector spaces, and then we'll go a little bit complex in time. So everybody knows Rn, right? So here in Rn, x is n tuples, right? x1, x2, all the way to xn. And the length of this vector, x, is, everybody knows that, that is the square root of the sum of the squares of each element in this tuple, right? So everybody knows that. So, well, in Rn, so we have a concept of length, and everybody is familiar with that. But generally, if we have a general vector space, we should have something similar to the concept of length. So think about length. Length cannot be negative, right? It can be 0 or positive, but it cannot be what? Negative. There are certain properties of length. So we need similar concept with similar properties, and we call it what? Norm. So we are going to define norm for vector spaces. A norm for a vector space V is a function. Well, length is a number, right? Length is a real number. So norm will take a function, like will take an element of vector space V and take it to real numbers. Okay, so a norm is a function that takes an element of vector space V and take it to real numbers. And it has three properties, just like the properties of length. Norm is bigger than or equal to 0 for any element of vector space V. And norm is 0 if and only if the vector is 0. That is the same as length, okay? The length of a vector is 0, that vector must be the 0 vector. And the length is always what? Bigger than or equal to 0. So the norm is always bigger than or equal to 0. And if it is 0, that means the vector must be equal to what? 0. All right? And if you multiply vector x with a scalar alpha, and then take the norm, the same as multiplying the norm of x by the absolute value of the alpha. This is similar to the length again. Well, when we talk about length, if you have this as x, this as a y, and then you have x, y, this is x plus y. And we know that the length of x plus y is what? Is less than the length of x plus the length of y, right? So similarly, the norm of sum of two vectors is less than the sum of the norms, the sum of the norms of the individual vectors. So if you have a function that satisfies those three properties, that's simply a norm. A norm is a function, okay? All right. So very well-known norms. We have Euclidean vector norm. Everybody knows that. If you have a vector in Rn, Rn is our vector space V. X is an element in that vector space. The Euclidean norm is defined as what? The sum of the square root of the sum of what? Individual elements, squares of the individual elements. So the norm is basically the length of this vector right there. Okay. Well, this is called, by the way, true norm. This is called true norm because of this square right here. Okay. But we generally have P norms. For example, for Rn again, you can define the P norm as this statement right there. So first get P power of each individual element, add them up, and then get 1 over P power. Okay. So if P is 1 here, as you see here, P is equal to 1. If P is 1, what does it mean? This is called X1 norm. And X1 norm gives us a diamond. What does that mean, actually? What does that mean? If you pick a point here on this diamond, and if you get this point, X, and if you get X1 norm of this point, or if you pick another point here, and if you get x1 norm of this point, any point on this diamond have exactly the same P1, exactly the same 1 norm. Okay, for example, here we have x1, x2, x3, right? This is in R3. And if you pick one point here, or here, or here, here, doesn't matter. Wherever you pick a point in this diamond shape, they will have exactly the same 1 norm. Okay. And how much? 2 norm. 2 norm. In this case, we say P is what? 2. Well, 2 norm corresponds to a sphere. For example, if you take any point on the sphere, any point in this sphere, they will have exactly the same 2 norm. Okay. Of course, for example, if you have a larger surface, for example, if you have like larger sphere like this, that means if you take a point here, a point here, a point here, they have exactly the same norm, but their norm is of course larger than the points on the inner sphere. Okay. And then we have infinite norm. Okay. If we say P is infinite, in the infinite norm, what we define is that, oops. Hold on one second. And in this one, in this infinite norm, what we do is that we get the maximum of the elements from the tuple. And why does it correspond to this cube? Or, you know, this, because, well, if you get any points here, any points here, any points here, any points on those surface, you're going to end up with the same infinite norm. I hope this is clear. I mean, if you can stop the video and spend a little bit of time, you will fully understand that, okay? So my question, or the question I would expect that maybe you can ask, are there any vector spaces for which we cannot define any norm? So norm seems to be, you know, definable for any vector space, right? Well, yes, for every finite dimensional topological vector spaces, you have a norm. But you may not fully understand the statement I'm going to say right now, but there are infinite dimensional topological vector spaces that may have a norm, but that norm may not induce the topology of the topological space. So that means there are some infinite dimensional topological vector spaces that do not have a norm that induces the topology of the topological space. So just keep my statement here when we discuss topological spaces, it may make more sense to you. So let's see what a subspace is. So before we can introduce some interesting vector spaces, first I want to introduce the concept of subspaces. Well, what was a vector space? A vector space was nothing but a set, right? But of course, a set with certain addition, vector addition, and scalar multiplication operations. So a vector space is a set with certain vector addition and scalar multiplication operations. Similarly, if we have a subset of this set, let's call W. W is a subset of V. Okay. If W is a subset of V, and if W is also a vector space with the same vector addition and same scalar multiplication operations, then W is a subspace. So W is a subset of V, and W has exactly the same addition and scalar multiplication operations as V. Well, in order to check if V is a space or not, we have to check those 10 axioms, right? Well, if W is a subset of V, and if we know that V is a vector space, if we already know that V is a vector space, and if we already know that W is a subset of this set V, then we don't have to check those 10 axioms. all we need to check is the closeness with respect to vector addition and scalar multiplication. In other words, a subset W of V is a subspace if for any alpha and beta and for any V and W, if the linear combinations of V and W with alpha and beta is in W, then that's a subspace. Again, I repeat, pick any elements, any two elements from W, and pick any two scalars and find the linear combinations, those linear combination of V and W with alpha and beta. And if that linear combination is in W, then W is a subspace. Or you can do individually, pick V and W, pick V and W. If you add them up, V plus W, and if V plus W is in this set W, then it is closed with respect to vector addition, and then get any scalar alpha and any vector V. If alpha V is also in W, that means that's also closed with respect to scalar multiplication. Okay. So what is a subspace? Well, think about R3. This is R3, right? This is R3. Think about a line that passes through origin. Okay. Well, line is in R3. In other words, line is a subset of R3. Okay. And if you take any 2 points on the line, if you add them up, it ends up on the line again, right? That means that's closed with respect to vector addition. If you pick any point and on the line, if you multiply it by 5, 6, 7, if you multiply it by a scalar, that point is still what? On the same line. That means that's closed with respect to scalar multiplication. In other words, a line in R3 is a one-dimensional subspace of what? R3. Why is it one-dimensional? Because any point on the line can be uniquely identified or uniquely represented by just a single vector right here. For example, this point is maybe 5 times this vector. This point is maybe negative of this vector. Maybe this time is negative 2 times this vector. So only one vector is sufficient to represent all the points on the line. That means there's only one basis vector. And the number of basis vectors determines what? The dimension of the space. Therefore, since we have only one basis vector, the dimension of this line is what? 1. Okay. Another subspace is the plane. Think about this plane. That plane is a subset of what? R3. Plane exists in R3. That's sure. That's for sure. And if you take any 2 points, this point and that point, if you add them up, for example, here, this is 1 point, this is another one. If you add them up, you're going to end up with another point that's also on the plane. That means that plane is closed with respect to vector addition. Or if you take any point, for example, this one, and if you multiply it by a scalar, you're going to end up with another point on the plane again. So that means the plane is closed with respect to scalar multiplication. Since it is closed with respect to vector addition and close to with respect to scalar multiplication, that's a subspace. What is the dimension? Any point, for example, this point right here, can be represented by any 2 vectors in the plane. Any point in the plane can be represented if you pick any 2 vectors in the plane, of course, nonlinear, okay? They are not going to be on the same line. Then any point here can be represented, for example, this point can be represented with unique combination of those 2 vectors. So therefore, the basis has 2 vectors, and the number of vectors in the basis determines the what? The dimension of the vector space. Okay. So now let's get a little bit more serious. Consider trigonometric polynomials. When I say trigonometric polynomials, finite linear combination of exponential functions. Well, I hope you know that, you know, sine, cosine, those functions, trigonometric functions, can be represented as exponentials. For example, here, this is a trigonometric polynomial. Why? Because it is finite linear combination of what? Exponential functions. For example, here, from n1 to n2, we have finite linear combination of what? Exponential functions. All right. Okay. Well, I mean, I suppose you already know, or if you don't know, I can tell you this. E to the I kx is equal to cosine kx plus I sine kx. In other words, an exponential is nothing but a representation with cosine and sines. So that's why we call trigonometric polynomials. We can show that trigonometric polynomials forms a subspace of L2 from negative pi to positive pi. Remember L2? L2 is a vector space, the space, a set of functions whose energy in one period is finite, okay? So this is reminding to you, L2 is a space of functions from negative pi to complex numbers whose energy in one period is finite, okay? So now we are going to show that the set of polynomials is a subspace of what? L2, okay? So, well, let's see. The set S of trigonometric polynomials is a subset of L2. Well, it's clear that's a subset of L2. Polynomials are continuous functions, right? Polynomials are continuous functions. And if you take an integral of any continuous function from negative pi to pi, it's going to be a finite number, okay? Or if you get the energy of that polynomial, yeah, so that's going to be finite, clearly. Or, I mean, you can just check this. Well, I guess I do right there, actually, here. If you get negative pi to pi, if you get the trigonometric polynomial, and if you do a little bit simple manipulation here, you can see that that is a finite number. And if you take two trigonometric polynomials, hx and fx, and if you get linear combination of them, if you add them up, obviously you're going to get what? Another trigonometric function. And if you get, sorry. And if you get any hx, okay, and if you multiply it with a scalar, and then you're going to end up with another trigonometric function clearly. So that is closed with respect to vector addition. If you add two trigonometric functions, you end up with another trigonometric function. If you multiply any trigonometric function with a scalar, then that's going to be what? Also another trigonometric function. So that's also closed with respect to scalar multiplication. Therefore, that's a subspace. So set of trigonometric polynomials or functions is a subspace of what? L2. Closed subset. Well, let's talk about limit point first. In order to define closed subset, first we have to talk about a limit point. Assume V is a norm vector space. Assume V is a norm vector space. That means V is a vector space in which we can define a norm, okay? And W is a subset of V. I don't say subspace, that's a subset of V, okay? A vector f in V is a limit point of set W if there exists vectors, set of vectors wk in W that converges to f. So I say, think about a vector in V. Let's call it f. And if we have a set of vectors or sequence of vectors in W that converges to f, we call that f as a limit point of W. A subset W of V is closed if it contains all of its limit points. What does that mean? Let's see with an example and you will understand better. Think about real line. Real line is what? RV. And think about this interval 0, 2. Interval 0, 2 is W, which is a subset of real line, right? So V is R. And then W is 0, 2. We know that 0, 2 is in R, right? So V is R, W is 0, 2 interval, okay? 0 and 2 are excluded. So now think about Fk is 1 over K. Fk's are all in W. Why? For example, if K is 1, 1 over 1 is 1. If K is 2, 1 over 2, 1 over 3, and so on, 1 over 4, and so on, okay? They are all what? In W, okay? But think about 0. So Fk, as K goes to infinity, is going to converge to what? 0, right? So all of the Fk's are in W. However, they converge to 0 and 0 is not in W. Okay, I repeat, we have 0 in R, okay? And 0 is not in 0, 2. So we have an F in V, but that F is not in W. However, we have sequence of vectors in W, and they converge to this F, okay? But that F is not in W. Therefore, W is not a closed subset of V. I'm not saying open. I'm just saying is W is not a closed subset of V. Okay? I hope this is clear. So think about a limit point. Think about think about the limit points of W. If W contains all of its limit points, then W is closed. But with this example, you see that 0 is a limit point and 0 is not contained in W, therefore W is not a closed subset of V. Supremum, consider a subset A in R. Just consider a subset A in R, for example, 0, 2. A is bounded above if there exists alpha in R such that for all elements of A, we have that for all x in A, we know that x is less than or equal to alpha. Okay. So if A is bounded above, sup of A or supremum of A is the smallest of such alpha. Okay. And this is actually very easy. If A is not bounded above, then sup is infinite. Well, I can give you examples. For example, here, think about A as 0 this way. So A is in R, right? However, the sup of A is infinite because you cannot find an alpha such that all elements of A will be less than or equal to alpha. There is no such a thing. So sup of A is infinite there. However, if A is, for example, I'm just making it up, to 5, okay? And if you pick alpha as 5, you can see that all elements in A are less than or equal to 5. That means sup of A is basically 5. Okay, of course, all elements are also less than or equal to 6, but we are looking for the smallest of such alpha. Therefore, the smallest is what? 5. And then sup of A will be what? 5 in that case. Well, we do not only talk about sets, but we also talk about functions. Let's consider a function f from domain D to range to domain D to R, what does a range of a function mean? The range of function A is simply all values that this function will take in the domain D. So A is a set of the values of the function in the domain X, domain D. And then when we say sup A, we can say sup or supremum of A, the same definition that is used for the sets. Sometimes sup or supremum is attained, that we have a maximum value of the function, sometimes we don't, okay? For example, assume that we can find an x0 in domain D such that the supremum value is exactly the function value. For example, the sup of this set right here, the sup of or supremum of this set corresponds to exactly a function value, then we say that's the maximum value of the function. Here's an example. F of x is negative x cubed for 0 to 2. Well, what is the sup or supremum of fx in this? Well, think about all values that f of x can have in this domain. And they are ranged from what? You can tell me, for example, f of 0 is 0, and then it goes all the way to what? Negative 8. Negative 8 is not included. So this is the set, right? The set is negative 8, sorry. The set is negative 8 to 0, like that, right? And the sup of this set is what? Or the supremum is clearly what? 0. Supremum of this set is 0. Well, we also have f of 0 is 0. That means sup is attained by this function. However, if you consider x cubed in this interval, okay, then the set will be what? From 0 all the way 8. The sup is 8. However, the sup is what? 8. However, we don't have any x0 such that fx0 is equal to 8. There is no such a value that we can have. Therefore, maximum is not defined in this case, and sup is not attained. So, I hope you are following me so far. Now we are going to talk about a vector space. Think about the closed interval AB of real numbers, of real line, that any continuous function attains its supremum. I mean, this is very clear, right? If you have any continuous function in AB, since it is continuous, this is the maximum, and maximum will be attained. So that's very clear. So there exists an x0 such that fx0 is the supremum of the range of the function. That's very clear. Now I'm going to consider a space of continuous functions. So CAB is the set of continuous functions from AB to complex numbers. Now we are going to show that C, set of continuous functions, is a vector space, and it has this infinite norm. Okay, I repeat, you can stop the video a little bit. What we are going to show right now is that the set of continuous functions is a vector space with the norm defined as this, the infinity norm defined as the maximum range of the function f in the domain A to B. Okay, I repeat, C is a vector space. C is a set of continuous functions, and it's a vector space with the norm defined just like here. The norm is the maximum value of the maximum of the function in that particular domain AB. So let's show that. The first thing is, first we need to show that this is really a norm. Sorry. So how do we show that this is a norm? Remember, the norm had three properties, right? First, we have to show that they satisfy all those three properties. So first of all, we know that's a well-defined. For example, norm cannot be infinite, okay? Since this is a continuous function and all continuous functions attains its maximum, that means maximum of f of x is well-defined. Property one, we need to show that the norm is bigger than or equal to 0. Well, it is bigger than or equal to 0 by definition because that's absolute value, right? So that's by definition. And then if f is 0, maximum of x is 0, right? Because if f is 0 function, if f is 0, this one will be clearly what? 0. Okay. Well, let's go and show this is this side. So f0 implies f infinity is 0. Now we need to show the opposite. If f infinity is 0, this must imply that f is equal to 0, right? So now let's assume that the infinity norm is 0. That means this maximum is 0. Well, if the maximum is 0, f must be 0 for all x values in the range. Otherwise, the maximum cannot be 0. So this implies that f of x must be 0 for all x in AB. Therefore, now we satisfy this and we also satisfy that. So f is, the infinite norm is bigger than 0 by definition, and also if f is 0 if and only if the infinite norm is 0. So the first property is satisfied. Second property, and now I'm going to multiply alpha f by a scalar. And that means I'm going to, multiply alpha there. Since alpha is a scalar and this is the maximum, I can take it out as maximum or absolute value of alpha. And then clearly this is absolute value of alpha times the norm, infinite norm f. So the property 2 is also satisfied. The second property was supposed to show us that this is equal to alpha and then f infinity. So that's also satisfied. The third property may be a little tricky because in the third one, we are supposed to show this. If we have two functions and if we add them up, the infinite norm must be less than or equal to infinite norms of the individual functions. So that's what we are supposed to show, okay? But what do we know? Let's assume that, well, we all know that if you fix x, okay, and then get f of x plus g of x, if f is fixed, then we clearly know that this must be less than or equal to f and g. For example, think about this. If f is fixed and if of fx is 3, if g of x is 4, we know that 3 plus 4 less than or equal to 3 plus 4. But if f of x is -3, g of x is 4, for example, we know that -3 plus 4 is less than or equal to what? 3 plus 4. So that's clear if you fix x. Well, since we fixed x, and we know that f of x for that fixed x must be less than or equal to maximum value of f of x, because that was any x. It's less than or equal to the maximum value of f of x for all x possible x's, and similarly gx for that particular value of x will be less than or equal to maximum value of g of x. Okay, and since this holds for any x, I just fixed x, I can fix x to anything. Since this will hold for any x, it must hold for the x that gives us the maximum of f of x plus g of x. So therefore, this clearly implies that. So basically what we did show is that f infinity is actually a norm, okay? And continuous functions are clearly a space, because if you take two continuous functions, if you add them up, you end up with another continuous function. If you have a continuous function, if you multiply by a scalar, that's also what? A continuous function. Therefore, set of continuous functions is a vector space, and with the norm that's just defined in the previous slide. Okay, think about a set of polynomials. Well, this may not look like a polynomial to you, because typically polynomials are supposed to be a to the k, b to the k minus 1, maybe c to the x plus maybe d, right? That's a typical polynomial. So this may seem like this is not a polynomial, but in fact, that's a polynomial, because you can decompose this one as 1 minus x times a polynomial of degree k, okay? And then, for example, here, this is 1 minus x, and then maybe a to the x to the k, b to the x to the k minus 1, and plus c x plus d. So basically, this can be decomposed into something like that. And then we have 1 minus x here, they will cancel, and then you will end up with a polynomial. So that's a polynomial, okay? Think about set of polynomials, f of k, and x is in between 0 and half, 0 and 1 over 2, okay? So let's think about those set of polynomials. And let's think about f of x as 1 over 1 minus x. Well, this is not a polynomial, clearly, right? So f of x is a set of polynomials. For every k, this is a polynomial, but f of x is not a polynomial. Well, what happens when k goes to infinity? Let's pause a little bit and let's see what happens when k goes to infinity, okay? First of all, let's think about the space, because polynomials are continuous functions, right? All polynomials are continuous. Let's think about the space of continuous functions. So C 0, 1 over 2 is defined as the set of continuous functions from this interval to complex numbers. That's basically it. And we know that the set of polynomials is a subset of this set, okay? We know that, okay? So note that f of k, well, this is not just the set of polynomials. Think about this. This is also continuous in this interval. It is not defined when x is 1, but 1 is not in this interval, right? So f and f of k are continuous functions. We already know that for a set of continuous functions, this is defined as a norm. We just showed that. Now, I want to ask you this question. If f of k is a sequence of functions, will we have f minus f of k with respect to infinity norm approach, will it approach to 0 as k goes to infinity? Okay. So basically I'm asking if the sequence of functions f of k is going to approach to function f as k goes to infinity. Okay. Or how do we measure that? Okay. So the question is, again, my question is, as k goes to infinity, what happens to the sequence of functions? Does it approach to f? The answer is yes. Okay, think about this. F of x minus fk of x. Well, what did we have? We had 1 minus k plus 1, 1 minus x minus 1 over 1 minus x, right? So what does this mean? And if we take the absolute value, this means this is equal to x to the k plus 1 over 1 minus x. So this is what we have right there, okay? All right, so now we know that this one is, each one is less than or equal to what? 1 over 2. So this is less than or equal to what? 1 over 2 k plus 1. But we know that this is what? Bigger than or equal to 1 over 2, right? And since this is a denominator, and it's so easy to show that this statement will be less than or equal to 1 over 2 to the k. And if you look at the limit as k goes to infinity, okay, well, this is for any fixed x, okay? But we know that this holds for any x, okay? Therefore, since this holds for any x, this inequality, it must also hold what? For the maximum of f of x minus f sub kx. That means this is also less than or equal to 1 over 2 to the k, but we know that this means f minus f of k with respect to infinity norm, and when we send k to infinity, this goes to 0. That means f minus f of k with respect to infinity norm goes to 0 as k goes to 0. Therefore, the sequence f of k converges to f. What does this say to us? What does this say to us? Think about w, a set of polynomials on this interval. And then clearly w is a subset of set of continuous functions because all the polynomials are continuous. So w is a subset of what? Set of continuous functions. Well, we know that this is a vector space. We know that this is a vector space. And we know that W is a subspace. How? Because if you have two polynomials, you end up with another polynomial. If you multiply a polynomial by a scalar, you end up with another polynomial. And then we also know that this sequence is in W because this sequence is a set of polynomials. And that sequence converges to an F, right? But F is not in W. F is continuous, but F is not a polynomial. So that means this sequence converges to an F, which is a limit point in that case, but F is not in W. What does this tell us? This tells us that W is a subspace of continuous functions. However, it is not a closed subspace. Okay? W is not a closed subspace of W. Okay, so we need to pause here a little bit and understand, remember the limit point concept and closed set concept. Now we have closed subspace concept here. So what did we show? We had a set of continuous functions, which is a space with respect to the norm, but it's important. That's a space and we define a norm, okay? Because convergence is going to be defined with respect to that particular norm. And then we define a W, which is a set of polynomials, which is a subset of what? Continuous functions. It's not only a subset, but it's also a subspace. And then we have a set of elements in W that converges to another element, which is not in W. So that means W is not a closed subspace of V. V is in this case what? C. So I hope you are with me so far. You can pause and, think a little bit. So we'll talk about Banach space, okay? Banach space is an important group of spaces okay? Well, my presentation is messed up here a little bit, but I will explain, okay? And in many areas of analysis, the spaces are often Banach spaces. Okay, we'll talk about what it is. But before I tell exactly what a Banach space is, I need to give you some motivation with convergence. Think about a sequence of elements in vector space V. Basically, we have V1, V2, V3, we have a sequence of vectors in vector space V, okay? That's all we have. Then we say that this sequence, Vk, converges to an element of V, okay? If Vk comes as close as possible to V as k goes to infinity, okay? So Vk gets closer and closer and closer to V as k goes to infinity. Or we say Vk goes to V as k goes to infinity, or V minus Vk in this particular norm goes to 0 as k goes to infinity. That means that that sequence of V sub k's converges to what? To V. Or limit as k goes to infinity, limit of Vk as k goes to infinity is V. So those three are equivalent way of saying that the sequence V sub k converges to what? The element V. So what does it mean? What does it mean? What does this mean? Okay. So basically, we want to make V minus Vk as close to 0 as we want by simply taking k sufficiently large. I can make for any epsilon, pick any epsilon. As long as you pick k large enough, the difference between the difference between the Vk and V in that particular norm will be less than that epsilon. Okay. For example, if epsilon is 0.2, then you can say V minus Vk will be less than 0.2 for, let's say, k is bigger than 1,000,000. Okay. But if you pick epsilon as maybe 0.01, then maybe V minus Vk will be less than 0.01 for k is bigger than or equal to maybe 1,000,000,000. Okay. So it doesn't matter whichever epsilon that you pick, no matter how small it is, you can always find an index k. You can always find a number capital N, and for all indices bigger than that n, the difference will be less than that epsilon. Okay, I hope this is clear. This is what it means, basically. Pick any epsilon, as long as you can pick indices larger than capital N, then the difference between Vk and V will be less than that epsilon. Okay? So the smaller the epsilon, the larger capital N, of course. Okay. So let's assume that we have this sequence of vectors in V, and if this sequence converges to a vector V, then we just said that for any epsilon or for all epsilon, there exists an N such that V minus Vk is less than epsilon for all k bigger than or equal to N. That's what we know. What's the problem with this? I mean, isn't it nice? I mean, you have a sequence of vectors in the space V, and then they converges to an element of V. What's the problem with this? Well, first of all, in order to analyze this, we must know what V is, right? We must know what V is. Or we must guess what V is. And this is not an easy thing. So when you do convergence analysis, it's very difficult to know what that V is, or you may not guess what it is, okay? So that's a big issue. So that means it's not easy to apply this definition, basically. How about Cauchy sequences? Well, this was for regular sequences, right? Now let's think about some special sequences. Let's assume that Vk is a sequence of vectors in V. And we say that this sequence is a Cauchy sequence if for any epsilon bigger than 0, there exists an index n such that the elements of the sequence gets as close as possible. Okay. For example, here, let's say that epsilon is 0.1. So then we say that there exists an n, maybe a million, I don't know, okay, such that Vm minus Vk less than 0.1 for all Km bigger than a million. So basically, as the index gets larger and larger, the elements of the sequence gets closer and closer to each other. Okay, so I am comparing the sequence elements with each other. Okay, so what's nice about this? Well, we don't have a V. We are just saying that the elements of the sequence gets closer and closer to each other as the index gets larger and larger. There's a theorem. All convergent sequences in a norm vector space are Cauchy sequences. Basically, if you know that you have a sequence that converges to a V, then you know for sure that that's a Cauchy sequence. But not all Cauchy sequences are convergent or converges to an element of V. That's an important difference, right? Not all Cauchy sequences are convergent in the space. So let's see with an example. Think about the sequence fx of n, like 1 over n, okay? So we know that, I mean, it's clear that limit n goes to infinity, 1 over n, this is gonna go to 0, right? So the sequence 1 over n, okay, converges to 0, right? And 1 over n, they are all in R, and 0 is also in R. So that means 1 over n converges to an element in R. And since it's a convergent sequence, we know that it must be a Cauchy sequence. In other words, for any epsilon bigger than 0, there exists an n such that 1 over n minus 1 over m will be less than epsilon for all n m bigger than or equal to n. That's really the case, right? As n and m goes to larger and larger, the difference between 1 over n and 1 over m will be smaller and smaller. So this is clear. Since this sequence convergence, that must be a Cauchy. But now think about another sequence or in irrational numbers. The sequence is this time 1 over n square root 2. Well, square root 2 makes it irrational, right? So this sequence is a sequence in irrational numbers in that space. But we know that this also, when n goes to infinity, 1 over n square root 2, this also goes to 0. Well, 1 over n square root 2 is in irrational numbers, but 0 is not an irrational number. You see that? So this is a sequence that doesn't converge to an element of irrational numbers, but we clearly know that this is a Cauchy sequence. Because with the same reasoning that I said here, you can pick any epsilon and you can pick an index n for which you can always find 1 over n square root 2 minus 1 over m square root of 2 less than or epsilon for sufficiently large n and m. You can always do that. So what do we say here? This is a sequence, this is a sequence that converges in R, therefore there's a Cauchy. However, this is a sequence that doesn't converge in irrational numbers, but we know that that's a Cauchy. Okay, so not all Cauchy converges, but all convergent sequences are Cauchy. Okay. Okay. So what's a Banach space? Now, a Banach space is a normed vector space. A Banach space is first of all as a norm vector space. That means it's a vector space with a well-defined norm, in which every Cauchy sequence converges to some element of V. Okay. So in the previous example, we had the space irrational numbers. We had a Cauchy sequence. It converges to 0, and 0 is not irrational numbers. So that's not a Banach space. Do you understand? So a Banach space is a norm-vector space V in which every Cauchy sequence converges to some element of that particular V. A norm-vector space V with the property that all Cauchy sequences are convergent in V is said to be complete, by the way. A complete norm-vector space is called a Banach space. Either you can use this definition or this definition. When you have a vector, norm-vector space V, in which all Cauchy sequences are convergent in that particular V. For example, irrational numbers, it was convergent in R, not in irrational numbers. So a complete norm-vector space is called a Banach space. Okay. So why is it good? Well, we know for Banach space that our analysis is going to include Cauchy analysis. So we are not going to deal with to find a particular, we all need to deal with the sequence itself. We don't need to deal with the limit points. Examples are complex numbers Rn or Cn, they are all Banach spaces. For example, the set of continuous functions or the space of continuous functions with this norm is also a Banach space. We can show all of those. And we can define LP. LP is the set of functions for which the infinite integral of the p power absolute value f of x to the power p is finite. And this is a norm, by the way, we call it P norm, defined like that. So this is LP space is a Banach space for P bigger than or equal to what? 1. Now think about Rn. Rn was collection of all n tuples, like x1, x2, xn. This is finite, right? So in Rn, an element x is just an n tuple, right? However, now we are going to consider infinitely many coordinates. Instead of finitely many coordinates, these are coordinates of this vector x. We are going to think about an x vector with infinitely many coordinates, okay? Here, and each coordinate is an element of R, okay? Then we define little LP space. Little LP space for this element, basically, little LP space consists of all such tuples, infinitely many coordinates, such that the energy is finite. Okay, so LP space, for example, if P is 3, L3n is basically all sequences k from 1 to infinity such that k from 1 to infinity x to the k to the 3 is less than infinite. That means that's finite. Okay, so these are called little LP spaces. And then little LP for P bigger than or equal to 1 are Banach spaces. Of course, with respect to this norm, okay? Well, so far we talked about the norm vector spaces, right? Norm vector spaces. Now we're going to talk about inner product of Rn, okay? So Rn is collection of all finite sequences. So we have X with collection of all finite sequences. This is Rn, right? Okay. And we can define the norm for this as we define like 2 norm or Euclidean norm like that. This is everybody knows. And we also can define an inner product of 2 vectors in Rn. Norm is defined on a single vector, right? Norm is a function, remember, that takes a vector to a real number, positive, it takes it to a positive real number, really. But inner product is basically what? If you take inner product of two vectors, for example, here in Rn, the inner product of x and y is defined as the element-wise multiplication of two vectors and then summation after that. Okay, well, if we look at here, and if I use this one, it is clear that x is equal to what? K from 1 to n, xk, xk. In other words, k from 1 to n, xk squared. And then this means right here, what? X squared. So from an inner product, you can always define a norm, if you can see that. So, and what is the inner product in R2, for example? Think about this. We have a vector x, we have a vector y. If you recall, the inner product of x and y is the norm of x times the norm of y, or the length of x, length of y, and then cosine theta. So the inner product is a measure of angle between vectors, right? So inner product is a measure of angles between vectors, especially as you can see in Rn very easily. So we need to define, remember the norm was a measure of length, right? Now we have angle concept in Rn. Now we are going to generalize this to inner product concept. An inner product on a real or complex vector space V is a function that maps ordered pairs of V and W to a real scalar or complex scalar. So for inner product, we need two vectors. In other words, let's think about this. The properties that we're going to have, just like from Rn, V, inner product V is real, and V inner product, because we know that V, inner product V is equal to what? V squared. So that means we know that that is bigger than or equal to 0. And we know that V, inner product V will be 0 if and only if V is 0. That's the first property. Second one is V, inner product alpha W is VW and alpha conjugate. If alpha is real, this will be alpha, but if alpha is complex, as you may recall, if this is a complex number, the conjugate of this will be A minus IB, okay? So that's the second property. That's the second property. This is the third one, distributivity. You can distribute like that. And for V, inner product W is the same as W, inner product V, if it is real vector spaces. If it is complex, you get the complex conjugate. So inner products, for example, in Rn, the inner product example is that. In complex numbers, C to the n, the inner product is x and then conjugate of y, element-wise. And Cauchy-Schwarz inequality is a very obvious inequality, actually. For R2, for example, we said that x inner product y is the length of x, length of y, and the cosine of the angle. And we know that cosine theta is less than or equal to what? 1, right? We know that. Therefore, if I take the absolute value of this, that means there, and we know that this is less than or equal to 1, that means this is less than or equal to x and y, just like that. And then this means inner product of x with itself. This is inner product of y with itself. So the Cauchy-sequent Cauchy-Schwarz inequality tells us that for a general vector space, norm vector space W, we have V, W inner product, absolute value is less or equal to inner product of V with itself and inner product of W with itself, of course, after square roots. And there is a little bit delay in videotaping this, so I'm going to, all right, so that's the Cauchy-Schwarz inequality for norm vector space V. In any inner product vector space, regardless of the inner product, we can always define a norm, as I just said. If V has an inner product defined like that, then we can always define a norm this way. That means an inner product space is a norm vector space. That's for sure. But the opposite is not true. We cannot always define an inner product from a given norm. We may define an inner product from a given norm if and only if the parallelogram law holds for the norm. What does that mean? This is the parallelogram law. If we have V and W, V plus W, the norm of V plus W plus the norm of V minus W squares, of course, is equal to, if this equality is satisfied, that means the parallelogram law holds. So if parallelogram law holds for all V and W, then we can define an inner space and we call it induced inner product. We can define an inner product, I'm sorry, when I said inner space, of course, right? We can define an inner product using this norm this way. So since we are using a norm to define the inner product, we call it induced inner product from the norm. So to sum up, from an inner product, you can always define a norm, but from a norm, you may not always define an inner product. You can define an inner product if the parallelogram law holds for that particular norm. Okay, so all inner product spaces are norm vector spaces, but not all norm vector spaces are inner product spaces. Now, Hilbert space. Okay, you may get a little bit confused, but Hilbert space is the best behaving space, by the way. A Hilbert space is a vector space with an inner product, which is a Banach space with respect to the norm, induced by that inner product. Okay, so a Hilbert space is an inner product vector space, and it's a Banach space with respect to the norm induced by that, by the norm from that inner product. Remember, a Banach space was a norm vector space in which all Cauchy sequences are convergent in that space. Now, Hilbert space is an inner product space, but if you use the inner product to define the norm, then that space is a Banach space with respect to that norm. A Hilbert space is a vector space equipped with an inner product such that when we consider the space with the corresponding induced norm, then that space is Banach space. I know it seems confusing, but it's extremely simple. Think about a Banach space. Banach space is a norm vector space. And all Cauchy sequences in that norm vector space converges to an element of that space. That's a Banach space. A Hilbert space is not a norm vector space. It's an inner product space. That's an inner product space, but it is a Banach space with respect to the norm induced by that inner product. Here are examples. Of course, Rn, Cn, these are like standard Hilbert spaces. There's a delay, so I'm going to stop the video and then continue. All right. So I'm going to give some examples of Hilbert space, and Rn and Cn are Hilbert spaces, of course. And then think about L2, little L2 space. Remember little LP space. This little L2 is a Hilbert space. but little LP is not a Hilbert space. For example, if you have L3n, this is a Banach space, but not Hilbert space. However, L2 is a Hilbert space, both Banach and Hilbert space, okay? So we must know this. Okay. So L2n is a Hilbert space with the inner product. The inner product of 2 is defined as this way, if it is complex inner product space. If it is real, don't worry about the conjugate here. So element-wise, product, and then summation of all the products. So the big picture one, we have vector spaces. Vector spaces may have norms. As I told you, there are some topological vector spaces in which we may not define a norm that induces that topology. So that means there are some vector spaces, they are not norm vector spaces. Then we have inner product vector spaces. We said that from every inner product we can define a norm, but not from every norm. We cannot define an inner product from every norm. We can define only if it holds, if the parallelogram law holds, okay? And then Hilbert spaces are inner product spaces. And then we have Banach spaces that covers Hilbert spaces, and Banach spaces are norm vector spaces. So that's our first big picture. Okay, I think it's worth to go a little bit more on this. We have vector spaces. They can be norm vector spaces or inner product vector spaces. Every inner product vector space is a norm vector space, but not vice versa. And every Hilbert space is an inner product vector space. Hilbert space is an inner product vector space. That's a Banach space with respect to the norm induced by that inner product. And there are some Banach spaces which are not Hilbert spaces, and Banach spaces are norm vector spaces. All the Cauchy sequences convergence to an element of the Banach space with respect to the norm. Okay, so now let's go to metric spaces. Metric spaces. So let's little bit back up and let's talk about the concepts. The inner product, it was what? A measure of angles. And then we had norm vector spaces. That was a measure of what? Length. Now we are going to talk about metric spaces. All right, so let's define a metric space, what it is. A metric space is a pair, VD, where V is a set and D is a real valued function defined on V cross V, such that for all V and W and V, W, and U in V, we have those conditions. The distance between V and W is bigger than or equal to 0, and the distance between V and W is 0 if and only if V and W are the same points. I mean, this is very simple, right? If you have V, if you have W, this distance will be larger than 0, bigger than or equal to 0, and it will be 0 if and only if V and W are the same points. And the distance between V and W is the same as the distance between W and V. And distance between W and U, for example, if this is V, if this is U, if this is W, this is the distance between VU, this is distance between VW, this is distance between UW. Of course, the sum of this two will be larger than what? This distance. So that's what a metric space is. Well, now if V is a norm vector space, then we can always induce a distance from the norm. For example, if V is a norm vector space, and if this is the norm, the distance between V and W can always be defined like that. In other words, every norm vector space is a metric space, but not vice versa, okay? Because from a norm, we can always induce a distance, okay? A norm vector space with this norm is a metric space with this distance. So every norm vector space is a metric space. Every norm vector space is a metric space. So topological space. Well, let's motivate this. Inner product spaces, we dealt with what? Angles. Or the analogy to Rn was what? Angles. And then norm vector spaces, the analogy was what? Length. Length is not as strong as angles. And metric spaces with distance. But distances are not as strong as length. So you can define distance between 2 points. And then topological spaces. Now in this case, let's think about what do we do if we don't have the notion of distance between elements, okay? So that's where topological spaces comes in. Maybe even if we don't know the distance between this distance between 2 points, we can still may say how close those points are, right? So, or we can define nearness concepts, okay? And that's topological spaces, basically topological spaces. In topological spaces, we have no notion. There might be some topological spaces with no notion of distance between the elements, but via neighborhoods concept or via open sets concept, we can define how close the points are to each other. But of course, closeness is not as strong as what? A particular distance. All right, so let's talk about what a topological space is. First, a topology on a set X is a collection T of subsets of X having the following properties. Basically, a topology on a set X is a collection of subsets of X with the properties intersection of any two members or intersection of any two subsets is also in this collection. Union of any number of members of T is also in T, and empty set is in T, and the whole set is also in T, okay? A set X for which a topology T has been specified is called a topological space. More precisely, it's an ordered pair, X and T. I repeat, you have a set X and a collection of subsets of X. You see, the nearness concept, how close things are going to be determined by some subsets of X. We'll see some examples, but before that, if X is a topological space with topology T, we say a subset U of X is an open set of X if U belongs to the collection T. Basically, the elements of T are called open sets of X. And the closeness or nearness will be determined by those open sets. Again, X is a topological space with topology T. When I say topology T, it is nothing but a collection of subsets of X. And the elements of, well, we say that a subset U of X is an open set of X if U belongs to that collection, okay? Because there might be some subsets of U that may or may not belong to that T. If that subset, particular subset belongs to T, we call it an open set. Okay, here's an example. Let's say that our set X is A, B, C. Think about this. A is a subset of that, A, B. Okay, this is a topology because this is a subset, this is a subset, it contains empty set, it contains the whole set. This is another topology, this is another topology. Well, how do we know that's another topology? Well, we need to go back and talk about properties. Intersection of any two members must be there, and union of any members must be there. So let's go ahead and check this. Think about this. A intersection AB is A, which is in T. So intersection of 2 is in T. And similarly, if we get A union, if we get 2, that's also in T. I know there's a delay in videotaping for some reason, so I'm going to stop and then continue. All right, let's talk about topological spaces. First, let's define a topology on X and think about the set X, okay? And that's a set. A topology is nothing but a collection of subsets of X, but the collection satisfies certain properties. For example, intersection of 2 members of T must be in T, and union of any number of members of T must be also in T. An empty set must be in T, and the whole set must be also in T. Empty set is a subset of X, and X is also a subset of itself. And a set X for which a topology T has been specified is called a topological space. More precisely, we use an ordered pair X and T. T is a collection of subsets of X that satisfies those 4 properties. And assume that X is a topological space with T, and think about a subset of U of X. If that subset U is in that collection T, then we call that subset U as an open set of X. And the neighborhoods or the nearness, closeness concept is all considered using that open sets. Think about A, B, C, the set, and we have 3 topologies here. And this is a topology. How do I know that that's a topology? And because, as I said here, we have A, AB, and if you take intersection, that's an A that belongs to T. If you have A union AB, for example, that's AB, and that's also in T. And if you do similar analysis for the others, 2 and 3, you're going to see that if you take any 2 elements, if you take intersection, and that's also in T. If you take any number of elements, if you take the union of them, that's also in T. And here, BC is not an open set here because BC is not included here. BC is an open set because BC is in T. BC is not an open set because BC is not in this. Okay, so I'm going to talk about metric topology. Think about X as a metric space and assume that we have distance function D, okay? Think about the balls that we define like this. This is X, this is epsilon, and the ball consists of all points Y in this ball, excluding the boundaries. So all points Y whose distance from X is less than epsilon is considered that ball, okay? Now, if X is a metric space with distance D, then if you think about the collection of all the balls B sub D for all X and for all epsilon bigger than 0, then it becomes a basis for a topology on X. In other words, using those balls, we can define subsets on X. And that's called the metric topology induced by D. I know it sounds a little fuzzy, but if you stop the video and read it carefully, you will understand. So therefore, any metric space is a topological space. So any metric space is a topological space. So here's the big picture. We have the inner product space, We know that every inner product induces a norm. So that means every inner product is a norm vector space. And we know that a norm induces a distance, and therefore every norm vector space is a metric space. And we also know that every distance induces a topology, and therefore every metric space is a topological space. And we know that there are some vector spaces. We know that there are some vector spaces that are not topological spaces. And this is the second big picture that I like to give to you. So these are some references, and if you have any questions, please don't hesitate to contact me. I know this might sound too much. There are a lot of concepts that you may not be familiar with, but I suggest you go slowly. This is our first week, so we'll be easy on you. We'll give you a little bit time to digest, and hopefully you can dive into your assignments. I'll see you in the next video.